también es un placer para mí presentar al doctor Alexander Kemper. El doctor Lex Kemper recibió su doctorado en física de la Universidad de Florida y pasó 2 años como postdoctoral en la Universidad de Stanford. Como también fue un Alvarez Fellow en el Laboratorio Nacional Lawrence Berkeley y se unió a la Universidad de Carolina del Norte en el 2015, donde es Assistant Professor. Durante sus estudios de doctorado y en su postdoctorado, Lex usó técnicas de computación de alto rendimiento para trabajar en superconductores basados en fierro, que fueron descubiertos en el 2006, por cierto, y él fue parte del equipo, ¿no? Utilizando Density Functional Theory y Quantum Cluster Methods. Y básicamente el doctor Kemper es un experto en computación de alto rendimiento para materia condensada. En particular, en 2018 recibió una beca de la Fundación Nacional de Ciencias de Estados Unidos para estudiar propiedades de 1 y 2 partículas en fases inducidas por luz en materiales de 2 dimensionales. También, desde el 2019, su trabajo ha transicionado a trabajar en la frontera entre información cuántica y materia condensada. Su objetivo es diseñar algoritmos que funcionen en las computadoras cuánticas de hoy o del futuro, que permitan solucionar problemas físicos interesantes que nos interesan, ¿no? Y la plática que nos va a dar el doctor Kemper hoy va a ser justo en el punto donde la información cuántica se une con la materia condensada. Entonces, es un placer para mí presentarles a Lex.
Muchas gracias, Blas. Bienvenido a todos. Aunque hablo un poquito de español, pienso que es más fácil para mí para hacerlo en inglés, entonces lo hacemos en inglés. Okay. Thank you all for being here. Thank you for the kind invitation, and I'm very happy to tell you about some of the things that we've been doing. Thank you all to the organizers for putting this wonderful conference together. Okay, good. My name is Lex Kemper. I'm at NC State University. Let's see, does this work? Yes. What I do, or what I did, was quantum materials in and out of equilibrium. We do this at NC State University, and for those of you that don't know, that is where we are. Well, right now we are here, yes. So this is Washington, D.C., and NC State University is over there in North Carolina. I have the good fortune to work with a very large number of good people. So this is my research group at the moment. They're all at NC State University, and I've got lovely collaborations sort of across the US and across the world. Okay, good. So what I'm here to tell you about a little bit today is about quantum computing and quantum information, just sort of an outline of where I think the field is, where the field is going, as sort of a bit of an introduction. Along the way, I'll tell you a little bit about what my group does and my perspective on how we do things. Okay, so if your news feed looks anything like mine, sometimes you see these kinds of plots appear. This is put together by some company that I don't know. But what they show is sort of the growth of the available physical qubits on the hardware produced by all these various companies today and projecting into the future. This is a really big, complicated hardware problem, and what's led to this rapid growth is that back around this time, right, this was really the domain of scientists sort of working in the physics laboratories, trying to figure out how to make these things happen. What happened around 16, 17, 18 is industry got interested. They decided this is not a problem of science, of physics, it's a problem of engineering. If we can just make better qubits, then we can do all these things. And that's what led to this rapid growth and the growth of all these companies that exist today. The reason they got interested is because, well, they're hoping to solve problems that are difficult. What is meant by difficult depends on who you talk to, but they're interested in medical things, they're interested in aerospace and defense things, finance, energy. This is sort of where I live in the materials side, but these are the reasons people are interested. And so companies like BMW and Honeywell and banking are all interested in trying to use them to solve their problems that are difficult. So this is from an industry perspective, right? I am not in industry. And so this is something that is more appealing to a scientist, right? Because what you do as a computational scientist is you take your problem and you ask a computer to solve it. Usually this is hard. And so as your problem size grows, the amount of time that you, or your graduate students, have to wait for a calculation grows really quickly, right? And a calculation that takes minutes I'm happy with, weeks starts to become difficult. It starts to become difficult to do science at this scale. So what we're hoping is that a quantum computer at some point will be able to solve problems that are beyond the reach of classical computers in some amount of reasonable time. Right? If I have a quantum computer that could solve a problem in weeks that would otherwise take me years, I would consider this a success. And so this is where we're aiming. This is where we want to go. It's not where we are yet. You can think of how the quantum computers work or are growing as kind of like a bespoke quantum simulator on one end, and where we want to go for some of these digital algorithms on the far end. And we're hoping to slide this thing across. For the time, we're here, where really what we have is you have some small quantum system that you can control, that you can try to simulate your favorite thing. It's not full purpose yet. It's supposed to be, but they don't work well enough. And so this is kind of like these cold atomic gases where you can try and configure them so that they simulate the system that you want. Over on the other hand are the sort of interesting industry problems, right? So airplane routing, there's a map, but you can't see it. Problems in medicine, problems in optimization, where do I put cell phone towers to provide maximum coverage? These kinds of NP-hard problems are where we want to be, but we're not there yet. This is what they look like these days. These are two different pictures of a quantum computer. This one is by Honeywell. What they have is they have trapped ions that go around here, like race cars, and they have them interact and do things. This one is the one run by IBM. Most of this is just a refrigerator. The quantum computer is this tiny black chip that sits over there. And for this one, they have on the order of 50 to 150 qubits. Not all usable, but that's sort of the scale that they have. Okay. So in order to have sort of structure for my talk, what I thought I would do is I would organize it along this famous paper. Like somebody said yesterday, nuestro amigo Feynman, who had these 4 questions. 1, can classical physics be simulated by a classical computer? 2, can quantum physics be simulated by a classical computer? 3, can physics be simulated by a classical computer, or a quantum computer, excuse me? And 4, can quantum simulation be universal? We're not going to do this one today, but we'll do the other 3. Okay, so we'll start with 1. Sort of clearly, the answer is yes. Yes, we do this all the time. And it doesn't mean it's easy, but it's a thing you can do. One example might be for the James Webb telescope that we launched, sort of last year, right? We have very nice astrophysical simulations about where this thing is going to be, how it's going to behave, for the next 40, 50 years. This is classical physics, and it's well simulated by a classical computer, and this is not too hard. This is hard. This is fluid dynamics, right? And so from easy things to, what is the interaction of one wind turbine with another? This is the solution of Navier-Stokes equations. It's a very hard problem, but it's nevertheless a thing that you can do on a classical computer. You can go download software to do this sort of thing. Okay, so yes, sorry. We can also do very simple things you might do in your classes, masses on springs. And just like the James Webb Space Telescope, this could be useful, right? Because in my field of condensed matter physics, you can use these kinds of things to think about lattice vibrations and how they affect your system. Okay, good. So that we can do. Can quantum physics be simulated by a classical computer? Well, let's think about that a little bit. And so we'll go back in history and we'll think about the very first sort of example that we know of in history of something called a magnet. This is magnetite. It's where the word magnet comes from. It structurally looks like this. It's got a whole bunch of iron and a bunch of oxygen interspersed. And even until sort of beginning last century, why this was magnetic was a difficult question. It was not easy. One solution to this was provided by Ernst Ising, or Ising, depending on where you're from, who wrote a paper called Contribution to the Theory of Ferromagnetism. And what he did is he reduced this model to sort of a simplified model of spins living on lattice sites. In this case, I've picked a 2D lattice, but it doesn't have to be. And this was actually quite successful. This model and extensions of it really did a nice job in describing how I go from something that's disordered magnet to a ferromagnet, to a thing that you would call a magnet. And so, you can build models like this. You can do this analytically for some models, and you can solve these. Now, we can think about this from a computational perspective, right? Each spin has two possibilities, up or down. If I have 2 spins, then I have 4. If I have 3 spins, then I have 8, 16, 32. And so this grows pretty quickly if you want to build a full Hilbert space for this. If I want 50 spins, this is how many I need. I don't know how to pronounce this number in any language, right? This is a lot. You could work out how much memory you would need. That's a lot of memory. That's larger than most supercomputers have available. And this is only for 50, right? This block of stuff has 10 to the 23 atoms. It has a mole, right? So this clearly doesn't scale in the way that we want to. Well, okay, maybe. But, nevertheless, there is a whole industry of folks doing precisely this. A lot of people in this room and talks that I saw this past couple of days, right, are on simulating quantum physics. So you can do this. I do this myself as well. Like, my group has done a whole bunch of work on quantum materials driven out of equilibrium. What that means is that instead of doing a measurement where you have your material and you look at it with X-rays or IR or UV, you go to one of these facilities. This is the LINAC coherent light source. It's really big. This is a highway. Right? This is a long straight building that used to be a particle collider, and these days what it does is it makes time-resolved X-rays. So you can look at the structure of a material, electronic lattice, as it goes in time. What that means is you get spectra, but you get spectra that move. And the hope then is by doing this kind of a dynamic experiment instead of a static one, that you learn something about your system that you otherwise couldn't. This is great. It's a very complicated experiment, and so naturally one has very complicated theory that goes along with it. That's the price you have to pay. There's a lot of theoretical tools that we use for simulating quantum physics. These are just some of the ones I've used. If you go look, this is one of the supercomputers at NERSC. If you go look at their list of software, it's very large. It's all for simulating quantum physics. For the non-equilibrium stuff, these are some of the things that we've used. Non-equilibrium, Green's functions, DMRG, exact diagonalization, all using these sort of high-performance computers. And it's great, but eventually they all fail. They run out of memory because you would like a larger system or a longer history. You run out of CPU time because you only have 2 weeks, right? And so eventually all of these things fail. The hope then is to say, well, this is 50 spins, that's too much memory, but that's also 50 qubits. And so then the hope is to overcome some of these issues by using a quantum computer instead of a classical one. Okay. The way you may think about using a quantum computer is very similar as you would a classical one, right? You take whatever your physics input is, whatever physical system is you're simulating, and then you have some kind of software stack that you've built, usually tailor-made for your problem. And this is the same in quantum computing, right? Except now we have hardware in addition to a computer. We have error correction and other complicated things. But in the end, what you want is you would like some dynamic observables, some static observables, some thermal properties. This is what you're after. Okay. So let me give you one example of how one uses a quantum computer to do that. This is one of our current workhorses as a field for how you solve problems in physics or chemistry, And it's based on a variational principle. You've probably heard this in your quantum mechanics classes. It says that if you find some energy, the ground state energy always has the lowest one. So your task is to find the lowest energy. How do you do this on a quantum computer? Well, you build a guess, an ansatz, where what you do is you take some parameters and you send it through, this is what we call a quantum circuit, or like it's a quantum process. You can kind of think of it like a Rubik's Cube. Yes, you are allowed certain operations. Not all of them, you can only do a few. I can't just take this cube and move it there, it's not allowed. Well, you could, but that's not what you're supposed to do. And by using your allowed operations, you would like to find a solution. Similar here, we would like to use these operations to find a state that has the lowest energy, whatever the global minimum is. This is the task. This is called variational quantum eigensolver, or variational quantum computing, and this is the basic idea. So this now sort of starts to head towards the realm of machine learning, right, where you want to optimize some cost function that you have. In our case, the cost function is dictated by physics because we care about what the minimum energy is. And we can actually do a bit better than a Rubik's Cube, yeah, because what I can do is I can measure the energy, I can measure gradients, and so I can use something like gradient descent. And so instead of a Rubik's Cube, it's more like you get some information about what is good and what is bad. So this we can do. This has been done by many people, but this is one example. So this is the group at IBM, where what they did is they built a molecular Hamiltonian. There it is. It's messy, it's complicated. And used a quantum computer, variationally optimize the various rotations that you make in order to obtain the minimum ground state energy for hydrogen, lithium hydride, and beryllium hydride as a function of their binding energy. This is now some years ago. This is 2019 or so. And as you can see, you know, the black dots are what you're supposed to get. The red lines are what they get, which for hydrogen works pretty great. This is because hydrogen is quite a simple system, right? So it's nice and easy to do. For lithium hydride, you can see it does an okay job here, a little bit bad here, and then something in the middle happens, which is because of chemistry. But effectively, it doesn't do so well in this region. Same story with beryllium hydride. You know, it doesn't quite get the minimum energy that you want. And this is very characteristic of quantum computers today. They're not precise. They have errors, and this is one of the things that we have to deal with. See? Okay. So can physics be simulated by a quantum computer? Yeah, it's where we're sort of headed. This is also where do we do some work? So I'll tell you briefly, tell you a little bit about what we've been doing in this area. So this is the framework for what we do. And usually it looks like follows, right? I would like to study some system, whether it's, you know, a spin model or a photonic model, or whatever you like. The usual process is I prepare the state, right? I find its ground state, or I find some starting state that I am happy with. And then I will time evolve it and look for some dynamical response, right? This is basically what one does as a physicist. So, you know, we've done a bunch of different things in this area. We've done subspace expansions, we've used some algebra, we've looked at open quantum systems. There's a lot of interesting things that you can do sort of on the back end with classical post-processing. And really what I'm trying to tell you with this is that there's lots of opportunities in this whole process for new ideas, new things that people haven't tried yet. Because this field is relatively new, it's interdisciplinary, and that means what you can do is you can take ideas that have worked well in your area of science and apply it here. Right, this is what I've done. I've taken ideas from condensed matter physics and effectively stolen them and put them over here and applied them over here, and sometimes they work quite well. So one example that this worked well in for is for correlation functions or response functions. What do I mean by this? Well, if I am, you know, I'm a materials scientist, I'm a condensed matter physicist, and what that means is I work with a lot of experimental colleagues. They work at facilities like this. This is the Advanced Light Source at Berkeley National Lab. This is San Francisco in the background. This is the most beautiful place to work. Like, you get amazing views. And this is a piece of, well, this is a superconductor. This is barium iron arsenide, right? And what your experimental colleagues do is they go and measure something. And everything that they measure, you can think about as a response function or a correlation function. It's always the following question. Given that I have some operator here, what is the amplitude for me measuring some operator somewhere else? No matter what kind of experiment you're doing, it always looks like this. You may change what the A and B are, or maybe you have A, B, C, and D, but they always look like this. From a condensed matter physicist, the ones we care about are photo emission, optical conductivity, that sort of stuff. Okay, so now as a theorist, your job is please go calculate these and then compare with my experimental colleagues. So what do? Well, you open up your many-body theory textbook, and what you find is you should do this. Okay. So you stare at this a little bit and you go, okay, well, let's see. Obviously, I need to prepare some states because that's what I would like to measure. That's the state I care about. I need to apply some operator. I need to time evolve this, right? Apply Schrodinger's equation. I need to apply excitation B, and then I need to do some interference and expectation value and that sort of stuff. So this is what you find in your many-body theory textbook, all of them. So you do that, and then now, instead of doing this classically, you're working on a quantum computer, and so you have to repeat this process. You have to first prepare a state, apply an excitation, time evolve, and do all the other things. In quantum circuit language, it looks like this. My purpose isn't to teach you how these work, but I'm sort of going to talk you through what these are. So I'll have my system, which has some number of qubits. I will use some of my Rubik's Cube to prepare the state that I want. I apply my excitation, I time evolve, and then I apply the other excitation. And then I have this additional stuff. And the additional stuff is there to make the quantum algorithms work. As you may know from quantum mechanics, you can't measure amplitudes, you can only measure probabilities, right? Born rule. And so this thing lets you get around that so you can measure amplitudes, but you have to work a little bit harder. So you can do this. So back in 2018 or 19 or so, I thought I would try this, and I tried this for a very simple system. I tried this for a Heisenberg model. This is just a system of interacting spins. Its ground state looks like this. It has high energy excited states where I can flip one, or it has these low energy states where they all sort of spin around together, and these are called magnons. So I tried this for a 4-qubit system. So 1, 2, 3, 4 with my 1 ancilla. So I needed 5 qubits, which doesn't sound like much, right? And here's what I got. Okay, so these are 3 different correlation functions you can measure. The blue lines and the red lines are what you're supposed to get. This is simple enough. You can work this on pen and paper. It's very easy. And so you can just work out what these are supposed to be. The dots are the data from the quantum computer. This is terrible. Right, look at that. This may be okay, but this just looks like it's flat. So what am I going to do with this? So I looked at this in 2019, and I was like, well, okay, clearly this is hopeless. Right, this is not useful for anything. But so, you can kind of tell that there are some frequencies present, and even here there are some frequencies present. And so we thought, okay, well, if I'm doing some experimental measurements, I never get 100% signal to noise either, so maybe that's just what we're looking at. So we worked a bit harder, did some error mitigation stuff, took Fourier transforms, and found this spectrum. So this is how much of a frequency do I get at a given momentum after Fourier transforming. And the red line is what you're supposed to get, okay? So I do find peaks where I'm supposed to. That's good. I also find the correct frequencies. This system, because it's small, has in these units frequencies of 0, 4, and 8. But I get them, I have subtitles, okay. But I get them in the wrong place. So I get some leakage from there to there. But nevertheless, even though the results are not perfect, you can still get useful information out back in 2019. And now this is not working anymore. Luis, what happened? Ah, okay, good, perfect. Yes, okay, good. Okay, and so here's where coming from a different area of physics into this space was useful, because I thought back to this, and I thought, well, what is this experiment really doing? It's taking a piece of material, it's hitting it with some light field. If you're doing X-ray scattering, it's X-rays. If you're doing ARPAs, it's photo emissions, one of these things. And then I have some excitation that propagates through my system, and in the end, I make some measurement. So rather than working with what you have in the many-body theory textbook, this is just some quantum process. I can simulate this. Okay? So that's what you do. You do the same thing. You prepare some states. But now you evolve under some excitation. You let the system go by itself, and then you measure at the end. And in this way, you're really getting the same thing, but from a different perspective. You need one fewer qubit, and that helps quite a bit. So we wrote a paper on this, and the whole idea is to make the excitation just part of the quantum simulation, and then do some post-processing in the end. So this is data, I'll show you a bit more in a second, right? But this is now a way that you can get around some of the restrictions and some of the difficulties just by coming at it with a new perspective. Just to give you an idea, sort of like the internal workings of how this works, right? So we start with some model. This really is just a toy model to play with to demonstrate that this works. It's called the Sushri-Verheeger model, and it's a simple charge density wave system. This is the kind of quantum circuit we put together and run. We've used some of our tools that we built based on Lie algebras to try and produce a small circuit as possible. This is because today's hardware is still very noisy, and you want a shorter circuit as possible because all your qubits decohere if you let them. Finally, for this particular method, we have a choice for what B is, and so we can make more complicated excitations. And so you measure all these for a bunch of different parameters, and now here's your data. It doesn't really look any better. No, this one looks okay, but these don't. But in this case, just one Fourier transform actually produces lovely spectra for these two. Right? And this is much better, not just because of the hardware, but because you have an algorithm that's more resistant to the kind of noise that exists. What happened here? Does anybody want to guess? No guesses? Okay. I have no idea. The hardware was having a bad day. I don't know. Sometimes you run the same calculation, it doesn't work. And then 2 days later, it does, right? This is some machine that sits in New York that I've never seen, that they calibrate every day, right? And some days it goes wrong. Still don't know what happened. Calculation is exactly the same, it's no different. Okay. Turning these into pretty pictures, at this point we can now actually produce what are nice spectra and represent the kind of physics that we care about. Not for a system that I care about yet, because this is easy, I can do this by hand. But the idea is to build an algorithm that works generally, test it out on something you know, and then apply it once we have some better hardware in places that you don't know. Okay, good. All right, so I told you earlier about bespoke quantum simulators. I am not the only person that does this. There's a large amount of people that do this. This is the IBM group that made some news by saying that they've done some fancy work on the Ising model. The rest of the community disagreed, but they can do lots of very large calculations at this point. This is from the Honeywell group where they did some non-abelian topological order with anyons. And so this is this thing that people are doing. They're using these as bespoke quantum simulators. But remember, we'd like to get here eventually, where I can do Schur's algorithm, factorize things, linear solves, and we're not quite there yet. If you go try and find, there's lots of theory papers and things that people have done on regular computers and pen and paper for this, but no hardware results. The reason is our quantum computers are not good enough yet. We need quantum error correction, which is a whole field by itself, where you can take the errors that naturally occur in your quantum circuit and correct them as you go. And what the field is currently doing is implementing this for the first time ever. So this is from a group at Duke. This is from Ken Brown's group, where they're measuring something. And what you're supposed to get is 1 all the time. So this is their raw data that you just kind of measured, and clearly you don't get 1 all the time. But if you apply this fault-tolerant correction, you can get something that's actually not too bad. Right, so we're just in the early stages of demonstrating that you can do error correction, and you can start to head toward what is called fault-tolerant quantum computing. Okay, so I started with this, and then I told you a whole bunch of physics things, yes? But most of these are not physics. So how does that work? Well, as it turns out, and this is a nice description of that, a lot of problems that are in the NP-hard class, in other words, things that are very difficult for a regular computer to do, can be mapped onto some type of Ising model. That's great, because what that means is that I can take all these things that I would like to do, where my solution space is too big and I can't do anything with it, and map them onto Ising models. And at that point, you can use all the things that you've done for physics and try and apply them to different things. So we can use the variational algorithms that I talked about, right? These now, if you put them that way, have applications in factoring, in principal component analysis, in data classification with machine learning, right? All of these things are now useful through this mapping. We're starting to get to the point where you can actually make useful hardware results for optimization problems. This is really hard to read, so I'll tell you what this is. So this is, they built an optimization problem. An optimization problem is like traveling salesman or knapsack problems or these things you learn about in computer science. And they ran this on, you can't read this, the D-Wave quantum computer. It's not quite the same as the others, it's an annealing machine. And they cheated because they took the problem that matches exactly the hardware. But what they were able to show is that they can get a better solution once the system size is big enough compared to a bunch of classical algorithms. And that's really the first time I've seen this. This is not something that, they've been talking about this for 10, 20 years, but is it the first time that a quantum algorithm has outperformed a classical algorithm? Okay, it's got a minimum noise floor. It can't get past that, and the classical algorithms can. Okay, this is for a problem where they cheated, right? The hardware matches exactly the problem. But nevertheless, it's a place where you can actually do that. So we're starting to show some progress in being able to do this. Why else do we want quantum computing? Well, there's lots of efficient algorithms. You may have heard about Shor's algorithm. In this case, what this is useful for is factoring large numbers. This is a very difficult thing to do, and if you had a good working quantum computer, you could do much better. What else? Remember this is a classical mechanics problem, right? This is supposed to be easy. Well, what has happened in the past year or so is that people have figured out that you can take classical physics problems and also solve them via quantum computers. This is one example of this, where you have some number of oscillators. Admittedly, you need a very, very large number of them before this becomes useful. But you can use a quantum computer to solve a whole bunch of classical oscillator problems. Similarly, fluid dynamics, or in this case, plasma physics, right, are also starting to be algorithms for differential equation solving of this type. Right, so we're starting to reach the point, and people are being very creative about this, where you can try and say, okay, well, I will have a classical problem. How can I cast this as a Schrodinger equation, for example, and then use a quantum computer to solve it? And this just keeps growing. If you go look on Archive for Quantum Algorithm, and you go year by year, this is what that looks like. This was 2023 back in June. So today, it's probably up here, and we'll end up over here somewhere by the end of the year. Right, so this is a really active field, and people are spending a lot of time being very creative about what they do. Okay, good. So we've answered our 3 questions. We've added one more. Can classical physics be simulated? All of these things are useful. I thought I would tell you maybe one more thing, and then I'll finish. Unfortunately, I've told you, a bunch of positive things, but all is not well. We have these things called barren plateaus. In all of the optimization problems that we care about, normally what you do is you go along some gradient and you try and find the minimum. And this is nice, except that our landscapes look like this. And so if you start in the middle here somewhere, where do you go to find the minimum? You have no idea. There's been some work showing there's no quantum advantage for chemistry, potentially, right? So what these folks did is say, well, let me look and see for some complicated molecules, is it actually helpful to have a quantum computer? And the answer might be no. We need some high levels of quantum speedup before we can overcome, the quantum error correction takes a bunch of extra work to do. And if you just have a quadratic speedup, it's not enough. You will be outpaced by this in resources. The quantum error correction themselves, I didn't talk about that, but it requires a whole bunch of heavy classical computing to go with it. And finally, I have circuits that I want to compile to something easy, and this is also a very hard problem. It's an NP-hard problem. So there's a lot of work to be done and problems to overcome, right? But we have resources, and you all have resources for this, right? There are people that work in optimization, quantum chemistry, right, graphical calculus, and so really this is an opportunity for basically everybody that wants to try and make an impact and use the things that you know to try and make life better for everybody. Okay, so this is what I told you about, right? This is where we are. Hopefully we'll get somewhere. We may be able to solve some of these problems in the future, maybe not. Maybe at a minimum we'll have something that solves interesting physics problems, and I would be pretty happy with that anyway. The last thing I wanted to say is I'm at NC State University. We have a relatively large department. We've got 40 faculty members that work in astrophysics, biophysics, condensed matter theory, experiment, and an experiment as well. What have I not said? Nuclear, high energy physics, all sorts of things. This was a really nice day, and this is what our building sort of looks like. So, if you're interested, come talk to me, come check us out, send me an email, that sort of stuff. Okay, thank you for your attention. I'll take any questions.
Thank you, Lex, for this wonderful talk about what we can do, what we aim to do in quantum information theory using what we know from quantum mechanics and also some for other fields of physics. So I think we have enough time for more than a couple of questions, so yes, sir.
Thank you, wonderful talk. I was just wondering, what causes the hardware to have bad days sometimes? No, in the sense that, have you been able to quantify it? Is it temperature variations? Is it, these kind of external sources of problems?
Good. That's a really good question. Personally, no. And the reason I can't quantify this is the hardware that I use sits in New York in a lab that I haven't seen, right? And so these are IBM's quantum computers. Anybody can use them. You could go sign up today. They have free accounts, and you can just go play with them. But that also means, because they're cloud accessible, I don't have access to the hardware. Now, I know people that work on the hardware, and I know people that, are studying why are these bad some days, and a lot of times it's, automated calibration that went wrong, or something in the lab, because it comes with classical control hardware, some problem with the classical control hardware, and the next time they calibrate it, it gets fixed. But no, I haven't personally looked at it, but this is something that they are working very heavily on, because in the end, you can't have a computer that only works on Tuesday. You would like it to work every day. But it's a hard problem because you have quantum systems who don't like to remain coherent. By nature, they decohere. And so fighting against that is a hard process.
Thanks for the talk. What kind of methods you use for in Lie algebras for the time evolution? I see in one of the slides you use Lie algebras, but I mean why? It's useful in what sense? I don't know.
Okay, good. The question was, why do I use Lie algebras for time evolution? Sort of generically, Lie algebras naturally arise when you are considering, if I have some quantum state and I'm acting with some operator, where can it go? Right? The community of quantum control very much uses Lie algebras to do this same sort of thing. Now, for those of you that are not familiar with them, when you do the exponential of an operator, you know that you can't factor that. You get terms and more terms and commutators and commutators and commutators and commutators. Okay. This forms a Lie algebra. Why is this useful? Because Lie algebras have structure. And if you can make use of the structure that is inherent in your problem, you're always better off. And so what we did is we looked at how do we make use of the structure in this problem in order to make time evolution more easy to implement or implementable at all. I'm happy to tell you more at some point.
Thank you for your very nice talk. My question goes on the same line of the last one. I would like to know when you optimize your quantum circuit in order to make it more efficient, the Lie algebra techniques that you use there are standard ones or are part of an emerging art that quantum computing is developing to attach that problem?
Great. Usually the standard ones. Almost everything is done with SU2 to the n or subalgebras of that. So yeah, there's nothing too crazy yet. These are things people are working on.
And for example, do you know what when you optimize your circuit, do you know if there's a threshold value under which you basically have the optimum one, or that quantity is not known until date?
I mean, okay, so this is a general optimization problem, right? Like, if you're doing some optimization, how do you know you are done? Sometimes you know, right? If you're doing classical optimization, they do these bounding techniques where you can say, okay, it has to be within these numbers and then I'm happy. If you are doing this for, some chemistry problem, generically, no. You don't know if you're in a local minimum, and you kind of have to check and try, but you don't know a priori.
Hi.
Hi.
I have like a general question.
Please.
In your experience or to your knowledge, how far along are we in time to have a reliable quantum computer?
Okay, good. Maybe, what do you mean by reliable?
I mean that you are sure that you can apply the algorithms and have the same result every time.
Okay.
I mean, not
Yes.
like a lab. I mean, just like that.
Okay, great. Good. So the reason I asked what do you mean by reliable, yes, is that if you ask it to solve some linear systems of equations, you will not get an answer today unless it's really easy, period. Because, let me see, where can I have, let's see if I can find a quantum circuit that I have. Just to have something to look at. I made a lot of slides. Okay, good. So as you go, and you have to, you apply quantum operations, each one of them is a little bit wrong. In addition, while you are going, your qubits decohere. So any problem that is too big, you won't get an answer to at all. So this is why I wanted to know, what do you mean by reliable? Because this will reliably give you nothing for some problems. There are problems that you can get reasonable solutions for. This one, I don't know why this one didn't work. This is also hardware dependence, right? This was IBM's hardware. From what I hear, Honeywell is better. Like they will give you more reliable answers. But I'm not going to guarantee that we'll do that all the time. So I think it's close to have reliable results, but not, maybe in the next year or two. The other question is, can I use that for something useful? And that's a different question.
In that case, like, do you think how long, 50 years or
Yes? Okay. So it depends on who you talk to. I was talking to somebody last week who said, you know, having 100 logical error-corrected qubits in 20 years, he said 50% chance. I thought this was optimistic. From my personal opinion, we may never get there, right? But I'm a pessimist. Some people are optimists. That's okay, right? And it's nice that we have this collection of people. What I do think is that we are very close to getting something useful out. It'll come from physics, it'll come from chemistry, it'll come from one of these places. Maybe not for optimization, maybe not for these other things, but I think we're close to getting something that you couldn't get with the classical computer. I would say within 2 to 5 years, that's reasonable. Thank you for the question.
Hello. Thanks for the talk. This is going to be a more theoretical question to save an experimental solution. Can quantum computers can help theoretical physics for, I don't know, simulations, I don't know. Yeah.
Yeah. So you got it? Yes. The question was, do I have this correct? Can quantum computer help theoretical physics? Yes. Okay. Are you counting numerical simulation as theoretical physics? Yes. Then yes, absolutely. Yes.
Yes.
No, that is exactly what I'm working on, right? Like, how do I do numerical simulations, but do them on a quantum computer instead of a classical one? Yes, I think very much so. Thank you for the question.
I think we have time for a couple more questions.
Hello, thank you very much for your talk. I have a question about the beginning of your presentation when you were talking that for simulating a system of 50 spins,
yes,
you would need like 18 terabytes of memory.
18 petabytes, yeah.
18 petabytes. But using a quantum computer, we only need 50 qubits.
Yes.
So instead of the terabytes, only 50 qubits
yes.
are necessary. Okay, thank you very much.
And this is because from the like pure how big is my Hilbert space perspective, you need a logarithmic number of qubits. Yes, and so you undo the exponential growth in that way. And this is how you get from 2 to the 50 to just 50. Thank you. You're welcome. Thank you for the clicker.
What are other areas of physics where quantum computing can be useful besides condensed matter? Thank you.
You're welcome. I'm trying to think of an area of physics where it is not useful. Okay, so my colleagues that work on neutrino physics, they're using this. My colleagues that work on nuclear structure are using this. Maybe statistical mechanics, not yet. Maybe that's one of the harder ones, right? But even that, we're starting to get there. And so I think people are being very creative about how they do that, but I think it could potentially have an impact in kind of all areas of physics.
I think we have time for just one question. So, someone? Oh, I'm going.
Hey, thanks for the talk.
Thank you.
From the questions you asked and the answers you gave us, it can be seen that everyday classroom problem can be gnarly to resolve with a quantum computer. So is there a complexity threshold you can think of when a quantum computer can be required?
Okay. Is there a complexity threshold for when a quantum computer can be required? Okay. So can I interpret that to mean required to have a solution that will not take me 50 years? Right? Yeah, no, but like in principle, right? Like, I can always get an answer if I throw enough resources at a problem, right? Yes, there are complexity classes just like there are for classical computing, like NP-hard, NP-complete, right? We have similar ones for quantum computing. They are BQP and QMA hard and QMA complete and all sorts of things that I don't know about. Where what you can show is that, for example, for BQP, this is a place where quantum computers can get an answer in polynomial time, whereas that would take a classical computer exponential time. So there are thresholds. So there's different complexity classes, and then the question is sort of when do you start? How long do you want to wait for these things, and how much memory do you have available, right? So with classical simulations, I think we've reached a point where unless you make more clever algorithms, we are now out of time and out of memory. And so I think those places are places where you might want to look for your quantum computer to help you a little bit. Thank you.
Well, let's thank Lex for his awesome talk and answers to their questions. And
muchas gracias.
The organizers have a little gift for you. Oh, a thank you gift.
Thank you.
Thank you so much for joining us.
Gracias y
Thank
gracias
you
por el
so
regalo.
much for joining us.